Our last problem reads, a starship of mass 8 times 10 to the 6 kilograms and speed of 5 times 10 to the 5th meters per second with respect to the local galaxy is on a collision course with an asteroid of mass 1 times 10 to the 6 kilograms approaching with a speed of 9 times 10 to the 5th meters per second. If the asteroid makes an elastic collision with the starship's asteroid shield, what is the velocity of asteroid and ship after the collision? The asteroid approaches the ship. We want to look at this collision from the side. The asteroid makes a completely elastic collision with the starship. We're told that the mass of the asteroid is 1 times 10 to the 6 kilograms. It has a speed of 9 times 10 to the 5th meters per second. The mass of the starship, 8 times 10 to the 6 kilograms, with a speed of 5 times 10 to the 5th meters per second. The problem is to find the final velocity of the asteroid and the final velocity of the starship. Before doing this problem, review the section in your textbook on elastic collisions. Turn off your VCR now and try to solve this problem before watching its solution. We're going to solve this problem by applying the law of conservation of momentum and also by using the fact that in a completely elastic collision, the kinetic energy of the system after the collision is equal to the kinetic energy of the system before the collision. Before I plug in any numbers, I want to make some substitutions. We have some rather large numbers here, 10 to the 6 kilograms for masses, 10 to the 5th meters per second on our velocities. I want to make the substitution that 10 to the 6 kilograms, for the time being, we will simply let equal 1 unit of mass, and 10 to the 5th meters per second is equal to 1 unit of speed. 9 times 10 to the 5th meters per second becomes simply 9 units of speed, and 5 times 10 to the 5th meters per second, 5 units for speed. 1 times 10 to the 6 kilograms, just 1 unit of mass, and 8 times 10 to the 6 kilograms, 8 units of mass. Using those substitutions, we can write that the original momentum of the system is the mass of the asteroid, 1 unit of mass, times its speed, velocity, 9 units of speed to the right, plus the momentum of the starship, which is 8 units of mass, 5 units of speed to the left, and to the left I'm going to indicate by a negative sign. So minus 5 units of speed to the left gives us 9 minus 40, or minus 31 units altogether. For the kinetic energy before the collision, I write that the kinetic energy of the asteroid is 1/2 of 1 times 9 squared, plus for the starship 1/2 of 8 units of mass times minus 5 squared. And if you work this out, you get 40.5 plus 100, or 141 units of energy for the original kinetic energy. After the collision, let's say the asteroid has a velocity u and the starship has a velocity v, so that the momentum after the collision is going to be 1 unit of mass for the asteroid times u plus 8 units of mass for the starship times v. This will be its final momentum, and since the momentum must be conserved, that must be equal to the original momentum, which we have determined was minus 31. The kinetic energy of the system after the collision is 1/2 1 unit of mass times u squared plus 1/2 8 units of mass times v squared. This is equal to 0.5 u squared plus 1/2 of 8 4 v squared. And since in an elastic collision the kinetic energy, final kinetic energy, must be equal to the initial kinetic energy, this will be equal to 141 units of energy. Now, we have two equations here. U plus 8v is equal to minus 31. 0.5 u squared plus 4v squared is equal to 141. There are two unknowns, both u and v, and we have two equations. So we want to solve these equations simultaneously for the unknowns u and v. We have to eliminate one of them. I'm going to eliminate u and write that u from the first equation is equal to minus 31 minus 8v. And then substitute this value for u into the second equation here and write that we now have 0.5 times, and I'll put it in brackets, minus 31 minus 8v. That is to be squared plus 4v squared is equal to 141. Our next step is to square the quantity in the brackets. We have 0.5 multiplied by 961 plus 496 times v plus 64 v squared plus 4v squared is equal to 141. If I multiply through the brackets now by 0.5, I'll get 481 plus 248 times v plus 32 v squared plus 4v squared is equal to 141. And now I'll add the 4v squared to the 32 and bring the 141 over onto the left-hand side of the equation and write that we have altogether 36v squared plus 248v plus 340 is equal to 0. And we recognize here that we now have a quadratic equation. I'm going to simplify this a bit by dividing both sides of this quadratic equation by 36, and that will leave me v squared plus 6.89 times v plus 9.44 all equal to 0. So we have to solve this quadratic equation for v. In the standard form of a quadratic equation, we have that the exponent, or rather the coefficient of our v squared term, a, is equal to 1. The coefficient of our v term, b, is equal to 6.89. And our coefficient c is just equal to 9.44. And using the standard equation for solving that, I have that V is equal to minus B, that's minus 6.89, plus or minus the square root of B squared, which is 6.89, that quantity squared, minus 4AC, that's minus 4 times 1 times C, 9.44. I then divide all this by 2A, which is 2 times 1. Now, if you work out that calculation, you get two values for V. We get V is equal to minus 1.89, and also that V is equal to minus 5. Which one do we choose? The V is equal to minus 5 corresponds to a case where the asteroid misses the starship or passes through it. Minus 5 was the original velocity of the starship. So we're going to reject this solution as being trivial and use this one, that V is equal to minus 1.89. We can immediately solve for U. U is equal to minus 31 minus 8V. That would be equal to minus 31 minus 8 times minus 1.89. And if you carry out that calculation, you can find that U is equal to minus 15.9. Now, if we remember that we had changed some units here, we can write that V should be minus 1.89 times 10 to the 5th, our unit of speed, meters per second, and our U then should be properly written as equal to minus 15.9 times 10 to the 5th meters per second. All right. Both of these velocities turn out to be negative, indicating from our convention that that means that those velocities are to the left. So that's the solution to our problem. That is the last problem on our tape.